Dear students, welcome to this second lecture on optimal control. In the previous lecture, we have seen the optimal control problem for fixed boundary problems. And in this lecture, we will see various different types of boundary optimal control problems. So, here the previous lecture we have seen the fixed boundary problem in this particular way, that is initial time is t0, final time is capital T, and initial condition is x naught and final condition is x1, all of them are fixed. X of t0 is x naught, x of capital T is x1. So, all the values are fixed one. And the second type of problem which we will consider is the T naught and capital T both are fixed value, but the initial condition is fixed, x naught is fixed, but x1 can vary. There is a it is not a fixed value or fixed vector here. Here we consider the state variable is a vector in Rn. And the third type is the x1 is fixed, x0 and x1 both are fixed, initial condition and final condition are fixed, but the time is not fixed, capital T can vary, initial time is fixed, final time can vary. And the other type is if we consider the initial condition is fixed, x of t naught equal to x naught is fixed both of them, but the final time as well as the final condition both of them are not fixed. So, it can be any function of this type. So, various types of function can be considered, neither the final time nor the final position, both of them are variables here in the fourth case. So, in all the cases we would like to find a optimal control for the control problem of this type, x dot equal to x of t u of t. So, we have a control system of the form, we want to minimize a functional j. In the previous lecture we have seen the j is of the form f of x of t and x dot of t u of t and t dt. So, this expression, but in addition to that we can also optimize a expression of this form s of t etc. Okay, the final a function which is a function of the final time capital T and which can be minimized, whether it is a constant or variable, a function of s can be considered and the performance index or the cost functional J1 is defined like this, which is to be minimized or maximized. So, if these values are fixed, x of t and capital T both of them are fixed values. So, the optimum value of J1 with s or without s both will give the same control function u of t, because it will s is going to be a constant. Only if s is a variable, then the optimization of this with s and without s may be different, will be different definitely. So, for considering a cost functional of this type, it is required that the x of either the final position x of t or the final time t, they should be a variable or both of them are variables. So, we consider the control system x dot equal to f of x of t u of t t and the cost functional J1 equal to s of x capital T comma t plus integral of this expression x of t u of t and dt, and the boundary conditions are given by x of t naught x naught plus and x of t is free and t is also free, and it will include all the cases, all the 4 cases. We can take x of t is fixed, then t is fixed and both of them are fixed. So, all the 4 cases will be taken care by deriving a procedure for this general case. Now, ds by dt integral is given by this expression, it is well known, s at final position minus s at the initial position of this. And if you substitute because here J1 is defined as s at capital T is there. So, using this expression s at capital T is given by integral ds by dt minus s at the initial condition. So, we substitute that expression, we will get the expression j as integral here. Already f is there, in the place of s at capital T we will replace integral ds by dt minus plus s at the initial condition. So, we can substitute the expression here. So, consider the equation integral T0 to capital T ds by dt equal to s at the final time minus s at the initial time. So, that is given. So, let us take a new functional j of u given by integral T0 to capital T capital F plus ds by dt, and integral ds by dt from the previous step if we substitute we will get j is equal to integral T0 to capital T f of x comma u comma t dt plus replacing ds by dt integral as s at final time minus s at the initial time. So, now if you compare this j1 and j, only extra term is here minus s at the final position, otherwise both of them are the same, and s at the final s at the initial point t naught, it is a constant. So, by minimizing j, whatever control function we will get, the same control function we will get by minimizing j1. So, instead of solving this problem j x dot equal to f and j minimizing j with this performance index, we can do the minimization problem with the j of u of s, this expression as the performance index, which will be easy to handle. So, now ds by dt, because s is a, if you take s as a function of x comma t, x of t comma t, then it is del s by del x into dx by dt plus del s by del t. Here we note that s is x is a vector. So, the dash indicates that it is the transpose of the vector del s by del x. Del s by del x means it is del s by del x1, del s by del x2, these are the component of the vector, the column vector, and when we put the transpose it is the row vector del s by del x1, del s by del x2 etc. So, this vector is del s by del x transpose is this one, and x dot, it means it is the vector as we know x1 dot, x2 dot etc. So, and del s by del t is a scalar function. Now, at the optimum value we say that the solution of the problem, optimal solution of the problem is the solution x star of t is the optimum state and u star of t is the optimum control. So, at these two functions if you evaluate j, so we are saying that j u star is given by wherever x and u is there we will replace it with x star and u star in the expression j, and the equation x dot is replaced by x dot star equal to f of x star u star t. That means the given equation is we are substituting just the optimal state x star in the given equation. So, we get this equation and j is given by this at the optimal value. Now, at any other function, that is in the neighborhood of the optimum x star, we take x star plus del x star, if this is our x star function, then by adding x star of t plus del x star of t, we get a new function depending on the initial and final condition. If they are all fixed, it will be like this. If they are not, if one is a variable, then we may get some other expression where there will be variation at the end position also. So, depending on the 4 types of problem, we will get x star and x star plus del x star function. Similarly, u star and del u function. So, this can be added. So, now substituting this function x star plus del x in the given equation, the state equation, the first one, x dot equal to f of x. So, we get that is equal to f of x star plus del x and u star plus del u. Here the star should be cancelled. F is a function of x and u. So, it should be x star plus del x and u star plus del u. J of u equal to integral t0 to t plus del t at the, see, t is the final position and t plus del t is the del t is the variation in the final position. But if t is a fixed value, then del t is 0. So, here for the case, first case where the t is fixed, the del t will be 0, but this is a general procedure for all the 4 cases. So, we take a general variation for the final position t, t0 to capital T plus del t, and at the any function x of t in the neighborhood of the optimum control, optimum state, we substitute those values here plus ds by dt. In the place of the functional j, we are substituting, first we substitute x of t and u of t and subtract from the original value at x star and u star. So, now we take the augmented functional j suffix a at the optimal control u star. So, that is given by integral t0 to capital T f at x star u star, and everything is calculated at the optimal state x star, all these terms are calculated at x star, and in the neighborhood of x star, next we substitute j a at any u of t, that is u star is the optimum control and u of t is in the neighborhood of optimum. So, we substitute in the place of x, we substitute x star plus del x and u star plus del u, etc. So, wherever x star was there, we just add the variational function del x and del u and calculate the same expression for the j a function. So, now we define the Lagrangian as the function which is present inside the integral, the entire integral. For j a u star, the function is capital F plus del s by del x transpose into x dot, etc. So, this function we call it as L, and the incremental function which is evaluated in the neighborhood function, the whole bracket, we call it as L delta, superfix delta. So, now we find the variation between j a at u star and j a at u. So, we just denote it as j a at u star as integral L dt, j a at u as this expression, because there is a variation in capital T also, the limit, upper limit also will vary t plus del t and L delta into this expression. So, this can be split into t0 to capital T and capital T to t plus del t of this expression, and using the Taylor series expansion for L delta, then we will get the expression like this. The second term, integral t to t plus del t of L delta, is given by the value is approximately given by this expression. using the mean value theorem, that is calculating L delta at the final position t multiplied by the length of this interval, that is del t. So, that is approximately this value, because it is a very small variation del t, and we get this value for approximate value. Now, using Taylor series for L delta, we get the L delta will, as we have defined here, L delta is this expression. So, if you write the Taylor series for the function capital F and the remaining things, and collecting the first order terms only and omitting all the second order terms, we get this expression, and so L delta is this one. Okay. Now, the variation del j is J A calculated at u minus J A calculated at the optimal control, and that is nothing but integral T0 to capital T L delta minus L into dt. This L is not there, extra L into dt plus, as we have seen the previous slide, the value is L at capital T into del t. So, we get this expression. So, the variation del j is given by this expression plus L at capital T into del t. Now, we take the second term in this integral, del L by del x dot transpose into del x dot. So, del x dot can be written as d by dt of del x, sorry, this dot to be removed. So, d by dt of del x is this expression. Now, we integrate by parts these two terms, we get del L by del x dot into del x evaluated at t0 and capital T minus d by dt of del L by del x dot into del x into dt. So, this expression we get. Now, substitute this term instead of the second term, then the variation del j is obtained by this formula, that is integral del L by del x minus d by dt of del L by del x dot, its transpose into del x dt plus del L by del u, that is also there in the expression here, del L by del u into del u. We have taken the first term, for the second term we have taken this integral d by dt of del L by del x dot, del L by del u is also there. So, these three terms plus L at capital T into del t, that term is there, and this expression del L by del x dot into del x evaluated from t0 to capital T. So, this, so now it is evaluated only at capital T, because here we see that there is no variation at 0. When we take t equal to t0, the variation of x at t0 is 0, because the initial position is same for all the functions which we consider, there is no change in the initial condition. So, only at the upper boundary value capital T we evaluate this. So, this term is del L by del x dot transpose into del x dot t evaluated at capital T. So, this is our variation, first variation. Now, for the optimal control, the first variation should be equal to 0, del j should be equal to 0, that gives the necessary condition for the optimal control, and that can be obtained by the following. Further, we see that the lambda value we have to choose, it is at our disposal. So, it can be selected in such a way that the first bracket turns out to be 0. We select the lambda value in this expression del L by del x minus d by dt. If you see here the expression L is having the lambda value here, lambda dashed into all these things. So, first we select the lambda in such a way that this expression vanishes, del L by del x minus d by dt of del L by del x dot is equal to 0 by choosing suitable value of lambda. So, we get the first equation as the Euler-Lagrange equation, and then we can see that there is no variation in, because the variation we are considering only in the function, the x of t. The control function is not affected by the variation x of t. So, this is arbitrary here, del u of t is arbitrary. So, here del L by del u can be selected to be 0, that is our second condition we get. And finally, after equating the first term, it is already 0, the second term is also 0, only the remaining terms are del j equal to L at capital T del t plus this expression, that should be equal to 0. So, we get the condition, boundary condition as del j equal to this equal to 0. So, with this 3 A, B, C, if you solve a given optimal control problem, we will be able to get a solution x star and u star. So, which may turn out to be the optimal required control, because it is only necessary condition. So, the second variation should be considered to assert whether the solution obtained are actually optimum or not. Okay. So, but in most of the practical problem, this solution turns out to be the optimal control problem, that we will see some examples we will see later. So, now we will introduce the notation Hamiltonian, introduce the function h which is called the Hamiltonian, which is defined by capital F plus lambda. If we observe earlier, the Lagrangian function L is defined as capital F plus all these terms. Now, what we do is we just take those terms in which x dot is not there, the derivative of x. So, we take Hamiltonian as capital F function and del s by del t function, there is no x dot, and here lambda multiplied by the small f function. So, we just omit the x dot terms. So, that is called the Hamiltonian. Okay. So, if you define h in this way, then we will get L as the remaining terms to be added, L star equal to the h star function Hamiltonian plus all the terms which contains the x dot term. Okay. So, we write this expression, I think del s by del t is also included in this one, it is not included in the h Hamiltonian function. Okay. So, now we can easily see that already we have derived the necessary condition for the optimal control. One can solve the problem using this expression if the problem is quite straightforward or simple expressions are there, but a convenient expression is using the Hamiltonian function. So, after introducing the Hamiltonian function, we can convert all this equation A, B, C in terms of h. So, if we take the first one, Hamiltonian can be written in this form. Okay. So, here, so now we have shown that the conditions A, B, C are the necessary condition for the optimal control of the given system. Now we are interested in converting this conditions A, B, C in terms of the Hamiltonian function. So we can see that the condition B, that is del L by del U equal to 0, directly we can see that it is same as del H by del U equal to 0 from the expression of L. And similarly the condition A, that is del L by del X minus d by dt of del L by del x dot equal to 0, that is condition A. So now we replace it with the H function. So del L by del x, if you see the expression L, so del L by del x is equal to here, del L by del x will be del H by del x here, and then the derivative del square s by del x square and del square s by del x del t, that will come, and here there is no x involved. So this will be, the derivative will be 0. So we will get this expression del square s by del x square into x dot. Okay. So this expression we will get. Now the second term is d by dt of del by del x dot. So if you substitute here, del d by dt of del L by del x dot is d by dt of del L by del x dot will give del s by del x and minus lambda term will come, and when we differentiate it we will get del square s by the d by the total derivative d by dt of del s by del x is given by del square s by del x square into dx by dt minus del square s by del x del t and minus d lambda by dt. So this term. So if you subtract this two in the, if we substitute in the condition A, we will directly get this expression del h by del x equal to minus d lambda by dt, that is the condition E, second condition. Del L by del lambda equal to 0, that is same as del h by del lambda equal to x dot. From the expression of L we can verify. Further we get the boundary condition as this thing, as we have seen earlier, the boundary condition is C. So to replace that, this is the condition C, and which is equivalent to this expression. Wherever L is there, if you substitute the H function as given as given in this equation, we get this expression H plus del s by del t evaluated at capital T into del t plus del s by del x minus lambda star evaluated at capital T into del x t, okay, equal to 0. So this result we will prove in the next lecture, that is because this needs a proof separately, and which will be used for various cases, the 4 cases which we discussed for the optimal control. This is the key boundary condition for various this thing. Now we can easily see here, after proving this result, we can see that if there is no change in the final condition, if capital T is fixed, then del t is 0, and similarly if the final position is also fixed, then del x t is 0. But if one of them is having a variation, we will get a suitable boundary condition for solving a system of equation. So for finding the optimal control, in terms of Hamiltonian, we have the 4 conditions D, E, F and G, where G is the boundary condition for the solution of the optimal control. Now we will see an example illustrating this procedure. So let us consider the equation x dot equal to 2x plus 3u, and the cost functional is given by 1 to capital T 5 x square plus u square into dt, and the initial condition x of 1 is 0 and final condition x of t equal to x suffix t. So, there can be different cases, t can be fixed and x suffix t may be a variable. Similarly, x suffix t may be fixed and t is a variable, or both of them are variables and or both of them are fixed, 4 cases. So, in all these cases, how to find an optimal control for the given equations. So, here the Lagrangian is given by the Hamiltonian h minus lambda times x dot. If we compare the equation, L star equal to h plus all this. So, if we note that we have started with the cost functional j as s of x t comma t, capital T plus etc. But in this particular example, the first term s is not there. So, it is equal to 0, only the remaining integral is there. Here we get, this implies s is equal to, s function is 0. So, wherever s comes, we take the 0 function. Therefore, the Lagrangian is equal to h minus lambda x dot, where h is given by the function f plus lambda times small f, and where capital F is the integrand 5x square plus u square, and small f function is the 2x plus 3u. So, these are the equation. Now, we directly make use of the 4 conditions for the necessary condition for finding the optimal control. So, del h by del u equal to 0. So, if we take directly del h by del u, that is 2u plus lambda times small f. So, derivative is 3 equal to 0. So, this implies u in terms of lambda minus 3 by 2 lambda, and the second is del h by del x equal to minus lambda dot, this second equation. So, del h by del x will give 10x plus lambda times 2, that is equal to minus lambda dot, the second equation, and the other equation is already given in the question itself. So, we have got x dot equal to 2x plus 3u and lambda dot equal to minus 10x plus minus 2 lambda. Okay. So, in the place of u we can substitute minus 3 by 2 lambda. So, it is 2x minus 9 by 2 lambda. So, this 2 equation, and for the boundary condition we make use of this equation. H s is 0, therefore, h evaluated at capital T into del t and minus lambda evaluated at capital T into del x t. It is h function evaluated at lambda into del t plus minus lambda function evaluated at capital T into the variation of the final position equal to 0. Now, if the t is fixed, then del t equal to 0. So, only this will be the boundary condition. So, that implies minus lambda of capital T into del x d equal to 0, but the variation is arbitrary. So, this implies lambda of t equal to 0, and already we have given some initial condition x of 1 equal to 0. So, these are the conditions. We have these two equation, x dot equal to this, lambda dot equal to this equation with these two boundary condition. We can solve the system of equation and obtain the optimal control u, and then after substituting the optimal control in the same equation, we will get the optimal state value. So, we obtain x star of t and u star of t, because first we solve in terms of lambda and x, then by substituting the lambda value we get here u equal to minus 3 by 2 lambda. So, we get the optimal control, then substitute the optimal control in the first equation, we get the x star also. So, we can solve the equation in this manner. So, same procedure can be adopted for the if the x t is fixed and t is a variable, we can evaluate in a similar manner. So, different examples we will demonstrate in the next lecture, that is optimal control 3, and we will prove this result also, the boundary condition result, in the next lecture. Thank you.